Welcome to Lattice Developers Conference 2024. This section is implementing low-power FPGA-based USB designs. Your presenters are Peiju Chang, Product Marketing Manager from Lattice Semiconductor, and Venkat Rangan, Founder and President of TinyVision.ai. Good morning and good afternoon. My name is Peiju Chang. I'm Product Marketing Manager at Lattice Semiconductor. I've been with Lattice for the past 10 years, managing the video connectivity FPGA product line. Very happy to be here sharing with you our new release to market USB-enabled FPGA, and we welcome your feedback. And with me here today is our partner from TinyVision.ai, his founder Venkat. Venkat, would you like to say a few words to our audience?
Thank you, PJ. Welcome, everybody. My name is Venkat Rangan. I'm the founder of TinyVision. We've been around since 2018, and today we'll go over quite a few details of the Lattice Crosslink U FPGA that PJ talked about. TinyVision has been a Lattice development partner for a while. We're happy to be here. So thank you for the opportunity.
Thank you, Venkat. Let's take a look at the agenda for today. So we will go over the role of USB in the camera sensor connectivity use cases, and also how the Lattice Crosslink UNX is a perfect combination of hard USB block plus a low power FPGA. And then with that, I want to turn to the TinyVision.ai Venkat to introduce his system on module, as well as reference design and also the service and support he provides. We'll conclude the section with frequently asked questions. The industrial and automation camera market is expected to grow from $4 billion in 2024 to $8 billion in 2030. And all this is fueled by the increased adoption of edge AI enabled in these edge cameras. There will be more camera being built, and then there will be more automation processes that incorporate these cameras. So if you look at the dynamic on the manufacturing floor, industrial settings, you need a lot of flexibility alongside processing power for these edge AI-enabled camera modules. So there's increasing need for a USB solution because it leads to simplified deployment and also improved processing power for these industrial camera modules. When I say USB is going to be a big part of the sensor connectivity solution, we're referring to the Lattice Crosslink NX video connectivity family of FPGAs. So primarily the FPGA interfaces between a camera sensor module and the processor. As you can see in the picture here, the interfaces don't exactly match between the sensor and the processor. And the FPGA is often used as a flexible bridge that interface the sensor and the processor, as well as able to provide the processing needed in between, on these sensor data coming into the processor. So as part of the Lattice Crosslink NX portfolio, we offer various interfaces on the processor side. From the top, you see MIPI CSI2 and PCI Express being the short range option. These are best for system integration, board to board, very short distances between the processor and the camera sensor and the FPGA. And we grow into Gigabit Ethernet, which it provides a longer range and sometimes a multi-sensor type of deployment. And USB, which is the focus of the presentation, it is providing a mid-range type of below 1 meters and a lot of plug and play and flexible accessory type of use case associated with this interface. And it's going to be the primary driver to proliferate industrial sensors in the manufacturing site. When you look at all the options that we outlined here, you can see we compared the different aspects of these interfaces by looking at the bandwidth, the range they serve, the type of latency, and whether they're easy to use, and also where is the design fit. As you can see from the very top, the USB 3.2 Gen 1 by 1 interface has quite a bit of video connectivity bandwidth at 5 gigabits per second. It is low latency. It has plug and play capability, and the design fit is that it can be built into accessory. It's easy for an add-on, very good for the dynamic deployment that you need in a manufacturing floor. Let me summarize why we need USB and low power FPGA. The USB advantages we talked about in the previous slides already. It is the most successful interface in personal computer history. It is flexible. You can do plug and play. It can be easily accessorized. It is a popular interface for industrial sensor modules. Combine that with the low power FPGA from Lattice Semiconductor. We allow a compact form factor for these camera modules. Edge AI is taking off. You need more and more of these camera modules. You're going to cram that into a much smaller space. The smaller module, the less power consumption you have, the more compact you can build these modules. With the FPGA, you can now fully customize with ISP algorithms or Edge AI inferencing algorithm of your own, and that creates differentiating features for your product. Let's take a look at what the Crosslink UNX device has to offer. By the way, a lot of this information is already on the Lattice product website, so you can get more information out of that. I just want to highlight two specific features, which is the hardened USB interface, meaning now on a system design, you don't need any additional PHY chip or anything to interface with FPGA. This is truly a single chip solution, offering USB 2 and USB 3 Gen 1 up to 5 gigabits per second, PHY capability on an FPGA. And on the right-hand side, you have the always-on capability. This is the dedicated block, enable low power standby to less than 70 microamps in a typical use case. So this drastically lowers the average power during operation, as I will show you at a later time. The rest of the features, you can find them on the Lattice website, and this product is fully in production today. What this means on a system design level is in order to bridge sensor to processors, previously you have to first talk to an FPGA and go through a parallel interface to a USB bridge controller chip, and that pushes the USB out into the processor. With the Crosslink UNX device, you have integrated both FPGA and the USB bridge function into a single chip. This drastically reduced the design footprint and total cost of ownership. The always-on feature can lower the average power. It is a dedicated block that manages FPGA entry and exit from the standby state. There's a programmable standby period that you can set. So the product FPGA can wake at certain intervals according to a specification. So, and couple that with an instant on feature, can quickly load the FPGA back into operating state. You can restore the FPGA to its operating condition. And toggling between these two states offer up to 6 times the power reduction in a typical application. On the left-hand side, you can see that the upper part gives you the wake power level, and the standby is on the bottom. By averaging, cycling between these two states, you achieve much lower average power. The Crosslink NX FPGA family enables a broad range of applications. Those includes factory automation, medical imaging, consumer and PC cameras, test and measurement instrumentation. As you can see the block diagram on the bottom, we provide a bridge and interface between the sensor and the processor by offering the ability to process the data coming into the FPGA through an image signal processing feature. You can implement edge AI inferencing algorithms and also implement fast I/O capture functionalities generally found in test and measurement instrumentation. It is a very flexible video connectivity FPGA. Taking everything together and looking at the Crosslink NX family across the board, now we offer logic densities from 17K logic cells all the way up to 40K logic cells. We offer various memory sizes, with the most offered by the Crosslink U NX devices at 3.7. Various DSPs capabilities, but the most important thing is now the full portfolio of video connectivity FPGAs can support all different interfaces that we specified. PCI Express in the Crosslink NX40, Gigabit Ethernet support across the full density of devices, USB controller M5 integrated in the Crosslink U NX FPGA, and all offering bridging to the MIPI D5 interface on the transmitter and the receiver. And last but not least, the always-on block is offered on the Crosslink U NX devices. It is a comprehensive feature family for connecting between sensors and processor. To allow quick development and prototyping, we offer the Crosslink U NX evaluation board. The evaluation board uses a MIPI CSI2 connector to interface with the popular Raspberry Pi camera module. And also on the USB interface, we provide the Type-C connector to a PC or SoC that you'll be using as part of your design. The board also includes a configuration flash, 128 megabit, using the QSPI, so you can achieve instant on. This flash memory is accessible through the micro USB connector. We're adding more flexibility to the evaluation board by offering option of an external memory using HyperRAM via a daughter card expansion. So you'll be able to add additional memory to it by purchasing these daughter board options. It also provides the Lattice and its partners opportunity to build new daughter boards to enable additional applications on the Crosslink U NX device. I encourage you to visit the Lattice website. The link is down in the bottom, so you can learn more about the evaluation board. Just really want to summarize all the things that you can find on the Crosslink U NX device. Go visit the Lattice Crosslink product page. You can find everything you need to know about the device through the design software, which is the Lattice Radiant software used for RTL design, simulation, and place and route. The Lattice Propel is a tool for easy integration of the RISC-V soft processor design environment, and also integration with various IPs that we offer. And lastly, look at the two reference designs available for Lattice. One is the USB to GPIO expansion feature reference design, and also the MIPI camera to USB 3 streaming reference design. And with that, I want to turn the floor to our partner, Tiny Vision AI. Venkat, take it away.
Thank you, PJ. A short introduction to Tiny Vision. We are a Lattice development partner, and we provide design services to startups as well as other fast-moving organizations to help build edge products from concept through production. And that includes all kinds of stages of production. We really love building things, and that's really what our company is about. Focus on low power and good engineering, right? And we have deep system knowledge. That is what we really leverage so that we can build good designs. The way we achieve this is not by trying to do everything all at once, but we leverage partnerships with various companies such as Lattice as well as others, and to put together complete solutions. We're also active in the TinyML space and other educational communities. A little bit more detail on what we do. We do product definition and system architecture as part of consulting services. So all the way from paper napkin stage through figuring out what chips to use, sensors in low power systems. The battery is really important, conserving energy. So figuring out how to architect the system is critical. Right? We handle board design, firmware, and FPGA RTL in-house. On the AI and ML side, we help customers with figuring out data sets all the way through ML architecture, what models to use, as well as training and deployment. And that is critical because with energy constrained systems, it's important to have the right combination of everything. We have access to SMT machines locally in San Diego. That's important for building things quickly, right? That's one of our main strengths. The other reason that is important is there are some companies, there are some organizations that care about US built hardware, and so we are compatible with that as well. We also are very active in the community and education space. We hosted the TinyML Build series last year, and we have a series of open source hardware that is available on our website, the Pico Ice and Arduino, and the latest one is the Pico 2 Ice, which is based on the newly released Raspberry Pi Pico 2350 processor. So do go check it out. So as PJ mentioned earlier, video cameras of all kinds are used in industrial applications as well as at home, right? But if you just think about a few use cases, there are all the way from barcode reading, which is pretty simple. You guys have seen it everywhere, through figuring out automated fault analysis, counting objects, right? That's a very, very common thing. Figuring out whether packages have the right stickers on them. Security is a huge area. You want to be able to detect people and not just send blank images for somebody to count hours and hours of video, as well as industrial robotics type use cases. Right? All of these, the common factor is the camera, and most probably there is a little bit of intelligence associated with the camera itself. So let's talk about the Tiny Clunks 33, which is our name for the system on module. And obviously it's a play on the Crosslink U NX33 and Tiny Vision. So this is really a complete platform. It's not just hardware or not just software, not just IP. We've bundled everything together to make it an easy to use complete solution. Okay, so let's see what the Tiny Vision SOM has. The star of the show, of course, is the Lattice Crosslink U FPGA. It's right there. We ported a softcore RISC-V onto it, and that does all the coordination of the USB. It has 16 megabytes of flash, and the compute version has 32 megabytes of SRAM. There is a second flavor where we do not have the SRAM, and so we give you all those pins that are brought out on the bottom of the board, and that's called the connectivity flavor. So we get 14 differential pairs for that, right? And in terms of the interfaces that are supported, it's USB 2 and USB 3.2 Gen 1. There is no PHY required on your board. All that is handled by the FPGA. You need to apply just a single 5-volt power supply to it. All the other power supplies are taken care of on the board, and you can use these are overspecified. So in a typical application, you may not need to add any other power supplies on your board. You can take the 3.3 volt from here and 1.8 volts from here. Also, there is clocking is self-contained. We've taken care of the USB clock for you and also allow you to use your own clocking scheme for flexibility. In terms of frameworks, we support the Zephyr RTOS that allows you to really leverage the entire ecosystem. We'll talk much more about that in detail. And of course, Radiant is the Lattice toolchain for this chip, and SenseAI is the Lattice AI framework. In terms of we also support image processing and audio primitives using the StreamLogic graphical no-code RTL development tool. You can select from a whole bunch of different audio and video processing blocks and press a button and it creates RTL for you. And in terms of it being production ready, this is typical of a SOM. It's fully verified. It's pretty small. It's 1 inch square, just a little bit over an inch square. And we have developed an ecosystem of dev kits and other connectors that we'll go through. This is manufactured in the US, of course, for those who care. So the organization of the SOM is that we give you the power supply consists of 3 switches and an LDO, and these are 1 amp switches, so you can draw power from them because the FPGA itself doesn't draw as much power, so it can be pretty efficient. We give you full access to all the pins that are available, the JTAG pins, a bunch of GPIOs. So the compute version gives you 6 differential pairs, while the connectivity version gives you 14 differential pairs. Of course, the USB 2 and 3, and the flash and SRAM. Also on board is the oscillator, say a 60 megahertz oscillator that is required for USB. The banks voltages are fully programmable so that you can do glueless connections to 3.3 and 1.8 and any other voltages that are possible. So why did we pick a SOM? A SOM is something that's pretty commonly used in very complex chipsets. For example, processors, large processors tend to have SOMs. And obvious reasons are it's very easy to integrate it onto your board. All the complex work has been taken care of, so you get very fast time to market. The manufacturer of the SOM typically makes it production ready, so you just pop it on your board becomes less complex, and works very well from prototype through medium volume. Once you go to larger volume, you may want to do a chip down design. And the significant advantage of a SOM is you can, let's say next year some other new processor comes along, a new chipset comes along, you just replace it with the successive SOM. You don't have to change your baseboard as long as the interface stays the same. And by keeping it constant, there is a possibility of an ecosystem of developers of all kinds who can assume certain characteristics of the hardware. Right. Now, of course, it's one size doesn't fit everyone, and so SOMs tend to be designed with some 80 or 90% of the market in mind. And so if you're part of that remaining 20 or 10%, then you may want to do a chip down design. let's say the shape doesn't fit. For example, your camera is really compact, you may want to do a chip down design. And of course, there is margins involved in everything. Cost usually drives things at very high volume. So you may want to do a chip down design for that reason as well. And in that case, typically some vendors license out the design itself. This slide is conveying the same information in a graphical form and drives on the point that cost as well as time savings are available throughout the design cycle, all the way from system design through integration and testing. You, instead of building everything from scratch, you're leveraging the work that the SOM vendor has put in. We believe in building modular systems, and our dev kit is highly modular. The SOM plugs into it, and we provide basic infrastructure for programming, USB-C, so that you can plug into it, and very flexible clocking system that if the 60 megahertz clock that's on the SOM doesn't work for you, you can use a fully programmable PLL to go and generate all the clocks that you want. Provides 3 independent programmable clocks, a quick connector for I2C, and perhaps the most interesting thing here is the 2 syzygy pods, which are designed for high-speed connectivity. And we have a couple of boards that allow you to connect one to cameras as well as maybe input and output. And you can measure power on this, and that really helps development because we've settled on the 22-pin Raspberry Pi Flex, which is a very, very common standard. To help you see how compact this whole design can be, we've also are working on what we're calling a tiny camera reference design. That is to demonstrate how minimal your camera could end up being. The SOM plugs into a very simple 4-layer board, and the 4-layer board has a couple of LEDs, push buttons, the USB-C, as well as the programming capability. The programming is not strictly necessary, but it's there because it just makes it a complete system. So this is a reference design that supports 2 dual lane Raspberry Pi 22-pin Flex. So let's look into what the UVC IP itself looks like now that we know what the hardware looks like. So we've designed a data mover engine which doesn't care about the data that it's sending. So you stuff data into one end and it shows up on the other end in the host. And the way that we have designed it is we've specialized it for UVC, but we're not limited to UVC. And also we can transfer data in either direction, although our initial release is purely for one-way transfer, which is for high bandwidth at least, is from the device to the host. The other thing we have done is we've written RTL around the hard IP in the USB block, which allows very high bandwidth transfer. The way that you get there is not by involving the processor in the data path. The processor can be in the data path, but that's for low bandwidth and highly interactive type of work, like a serial port, for example. In terms of the RTL interface, there is the USB pads and clock and reset, and that goes straight to the pads. We use Wishbone. There's a 32-bit Wishbone control port that you hook up to the processor, and a 64-bit wide FIFO that's flow controlled per stream, and that's it. Right? Everything else is handled for you by the system. So getting more into the details of the RTL itself, we have followed a set and forget model where the RTL that wraps around the hardware, the hard USB IP in the FPGA deals with the data transfer itself. Only the control, which is the USB enumeration and negotiation, is handled by the RISC-V. Everything else is handled by the RTL. And this is pretty configurable. We can customize it for use cases if needed. The most common use case is UVC. That's what we're starting off with. You can see that the logic utilization is pretty small. we will end up with typically about 30% of the FPGA used for a base design, and you have the remaining about 20K lookup tables available for your use. In terms of memory utilization, this is a big one because on-chip memory is extremely valuable. We try to optimize so that we use as little memory as possible for this core. And in terms of achievable bandwidth, at the application layer, we have measured 3.4 gigabits per second, which is relatively independent of the frame rate. In terms of what we support on USB, that is pretty much limited by what Zephyr supports, and we are upstreaming our work on UVC as well as the USB 3. We support bulk UVC in endpoints today and the serial port for enumeration. So getting into some metrics, we measured 3.38 gigabits per second on multiple platforms, the lattice dev kit, as well as our own TinyVision Tiny Clugs song, which is pretty independent of the frame rate itself. So we've used test pattern generators to emulate very high frame rates. And it's also pretty low power, less than 200 milliwatts running full on, right? And this includes the entire FPGA power. So USB is a very complex interplay of FPGA RTL as well as Zephyr firmware. And to debug that is not trivial, right? And there are variations that happen not just on the device, but on the host side that can cause things to go haywire on the USB side, on the device side. Right? The way that we've designed the high bandwidth RTL really simplifies things, because once the USB RTL is kicked off, it's independent of the firmware running on the device. So all the control is handled by the RTL itself. So debugging it is much simpler, because now if you have decoupled the hardware, so you know exactly where to look for in the bug. And how do you actually debug a running system? So we use Zephyr, and we've written debug commands. So you can see some of that here. So USB 2.3 is really the command, the high-level command that lets us dump various kind of statistics, as well as the DMA descriptors, which are called TRPs, which really help us debug and figure out exactly what's going on inside the IP. So let's say we want even more information other than what the command line produces. How do you debug it? So Radiant has a reveal debugger, but that's not very real time, right? So what we've done is we've integrated a soft JTAG and push data out over that to pull actual hardware logs. So we have visibility into various parts of the USB IP. For example, there's a large FIFO that takes care of jitter in the USB link. So we can look at the visibility of the FIFO occupancy as a way to tell if something's going on. So out here, we ran an experiment on the left side without any hub, a direct connection from the Tiny Clunks dev kit into the processor, into the host. And on the right, a little bit later, we added a hub. Now you can clearly see that the occupancy of the FIFO is far higher once you added the hub, and that leads to significant jitter. This sort of data is very, very difficult to capture unless you have a USB 3 analyzer, which costs a ton of money. Right? So we are able to collect all the statistics and push it out over JTAG to help you debug the system. So we talked about complete frameworks. Now, how do you help somebody who's developing a smart camera? Because there are not that many Verilog developers or VHDL developers that understand image processing. So we've worked with Streamlogic, who's our partner company, and this is a completely graphical design tool. Uses drag and drop technology hosted on the web, and it's a data flow driven paradigm. right? So you can select various blocks from image processing, filters, all kinds of audio and video IP that are pre-verified for you that let you configure them and push a button and it dumps out RTL. You can test this on the cloud itself by uploading your blocks. And it covers not just audio and video, but also CNN blocks. So you can build your own things very, very quickly. You don't have to sit and code up things from scratch. So getting to where we are today, this is our status. We support single camera as well as two camera designs. Adding one more camera is not so difficult, and we will support that. In terms of Zephyr, we have started the process of upstreaming our work on UVC. The USB IP driver is going to be in a binary distribution, and the IMX219 Zephyr driver is open source, and that is also being pushed upstream. Right? And as other cameras sensors are added, they will be also part of the system. And as far as the sample designs that it works on, this IP works on the TinyVision SOM dev kit, as well as on the Lattice dev kit. And as other platforms come online, we'll be happy to support them. Now a question might come out, why Zephyr and why didn't you do bare metal? Right? Now Zephyr is very, very well supported in terms of a community. There's a huge number of drivers. It's very compact, well proven. So we decided early on that we do not want to be sitting and writing all the USB classes on our own, or even drawing from unknown sources. So Zephyr simply made it easy. However, our work didn't stop there, as you'll see in some of the next slides. USB has a philosophy almost that it should be simple to use, but the corollary of that is somebody has to face that complexity, and it's usually the developers. So USB devices are extremely complicated. Here's a little bit of an eye chart for you, right? So we've developed with the Cypress USB super speed chips that are supporting cameras today, that uses a ThreadX RTOS. And the USB descriptors for a single UVC, this is all the stuff, all the code that needs to be there, right? Let's say you want to add a second UVC stream. If you did that, this is all the highlighted differences that you would have to deal with. So it's pretty complicated. Why am I showing you this though? Which is on the next slide. We worked to simplify things, and that entire amount of complexity that you saw in the previous slide has been reduced to something that anybody can understand in the spirit of USB. Describe only the things that you need to, and everything is derived from that. So you can say, here is the name of the endpoint, what is the direction, and what is the format that you have. If you want to add a second UVC stream, you just add the highlighted portion here, which is very, very intuitive from a software point of view, rather than trying to deal with all of the changes in the low-level USB descriptors. At the end of the day, this ends up creating a whole bunch of code automatically. That is far better than trying to hand code it and then debug it. So the Zephyr device tree is an absolutely amazing thing. It looks a lot like the Linux device tree. Let's say you want to add an I2C temperature sensor. So the highlighted portion is what you would add, and all the drivers get taken care of. This doesn't mean it's actually trivial to generate a new driver for a new sensor. The hard work has to be done somewhere, but it's done in a different place so that users don't have to feel the pain every time you develop one. And all this gets pushed into the open source repos that Zephyr has. Let's say you want to add a multiplexer around a sensor. So it's this very intuitive way of adding multiplexers, for example. So you're cascading I2C devices. The selection of which device goes where now happens automatically. Similarly, if you want to add a UVC port as well as a serial port, it gets really simple. And all of the enumeration is taken care of by Zephyr in the background at compile time. This is the power of Zephyr and the power of the zero configuration approach that we've taken. Once you start using Zephyr, you'll realize there's a lot of data out there in terms of documentation, developers, what are all the protocols supported, and libraries, right? There's all kinds of scientific libraries, ROS is there, and just extensive documentations. So this is, in retrospect, a really good choice. So we're really happy to be supporting Zephyr. In terms of the TinyVision reference design roadmap, we have the two flavors of modules, the compute module and the connectivity module. We are currently building the Tiny Clunks camera, and in terms of applications, we have single camera UVC and multi-camera that is working. You can come and see the demos. We are developing ISPs as well as other onboard processing that is under development, and love to get your feedback. If you have any requirements, do come and talk to us. So we've tried to wrap a complete package, as I mentioned right in the beginning, consisting of documentation, technical support, as well as updates and maintenance, along with the license. We provide training if needed, as well as customization and tuning for specific use cases. For example, if UVC is not your thing and you want to send all kinds of other protocols, we're happy to support you on that. This is designed to be much more than an app note. Really, it is a reference design that is as close to production as makes sense for a company like us to put together. So what is included in a license, right? There's a single license to access all USB flavors, which is a single UVC stream or a dual UVC stream or even 3 UVC streams, whatever we come up with in the future. All of that comes under a single license. There is, once you go through the Radiant process, you'll find that there is an evaluation mode with a time limit. So customers can fully evaluate this system before purchasing. And in terms of pricing, we are going with a 1-year license with a 3-year commitment. And various options are available, and that would be a discussion we would have to have with each company, whether you want a site license or a single project. So in terms of an engagement model, dev kits and SOMs are available from our website. Go to tinyvision.ai and look up the store. The USB IP itself has been tested and is available for evaluation and licensing. We do provide design services to customize the SOM or to do chip down designs. One of our customers has already done that. And we do customize the RTL as well as firmware. The best way to reach us is really the email down here, sales@tinyvision.ai, as well as Discord. So thank you very much.
Thank you, Venkat, for your presentation. Let's go over some frequently asked questions. Where can I find technical information about the Crosslink UNX? You can find those on the Lattice website. We have all the collaterals, software information, and reference design that you need to start developing on the Crosslink UNX FPGA. The second question is, where can I buy Crosslink UNX and when is it released to production? The device itself is already released to production today, so you should be able to find them without distribution, Mouser, DigiKey, Arrow. So take a look at their website, should be able to find these parts. Third question is, what can I use to evaluate the Crosslink UNX devices? As we mentioned previously, we do provide the evaluation kit. It's a flexible board that you can use to start prototyping your application. As part of that, take a look at the SOM board and all the baseboard that tinyvision.ai put together. You should be able to reach out to both Lattice and tinyvision to start your evaluation. The fourth question, how can I start designing with the Crosslink UNX FPGA? So similarly, you always want to start with the software, which is the Lattice Radiant and Propel tool. You can download those tools from the Lattice website, and that should give you the ability to start designing the RTL, do some simulation, and then ultimately build a bit stream that you are able to program into the device. And to do that, you will obviously need a hardware kit, and that's what we answered in the previous question. So make sure you start with the software. The fifth question is, how much do Crosslink UNX devices cost? The cost of these devices is published with our distribution partners, so make sure you take a look at their website. Alternatively, you can reach out to the Lattice sales representative in your geographic region. And finally, if you don't know where to go check out the Crosslink UNX product website. There is a contact sales link, and that should connect you with our sales representative. And then the last question is, did Crosslink UNX pass USB certification? Yes, it already obtained the USB 2 certification, and the USB 3 certification is ongoing and will be completed by Q1 2025. So we'll keep you posted when that happens. So that concludes the section. Hope you learned a lot today. Hope to hear your feedback, and thanks again.